Among the mausoleums and memorials of the rich and famous of London's Kensal Green Cemetery lies the gravesite of Charles Babbage, noted mathematician, mechanical engineer, and inventor. His contributions and innovations during the Industrial Revolution helped shape the world we live in today. Charles Babbage was born on Crosby Row, London, England on the 26th of December 1791. His father, Benjamin Babbage, was a prominent banker of Prades and Company of Fleet Street. Early in life, Charles suffered a life-threatening fever which prevented him from attending school and was home tutored for a while, until he was about the age 15. He was enrolled at the Holmwood Academy on Baker Street. It was here at the Academy's library that he developed his interest in mathematics. He then left Holmwood, feeling that their instructions were lacking, at the age of 16 or 17, to study at the Totnes School, where he reached the level of study sufficient to be accepted at Cambridge University. Among the other young students at Cambridge, he forged a friendship with John Herschel, son of the famed astronomer William Herschel, discoverer of the planet Uranus. Together with several other friends they formed the Analytical Society. At Cambridge he was the top mathematician, and after graduation, Babbage's career continued to blossom. In 1815 he lectured at the Royal Institution of Astronomy, and he was elected to the Royal Society in 1816. In 1820 Babbage helped in forming the Astronomical Society of London, better known today as the Royal Astronomical Society. Its goals included reducing astronomical calculations to a standardized form of mathematical charts and tables. He and Herschel worked together on the project to recalculate the errors found in those calculations. It was during this time that Babbage began to formulate his concepts for the use of mechanical computations. The Industrial Revolution, which began in Great Britain in the 1760s, and by the 1820s, it had spread across Europe and the United States. Manufacturing and transportation, departing from handmade products to machine production, and through the use of steam and water, to power mechanized factories, which significantly increased production. The invention of the steam locomotive changed transportation, by greatly reducing travel time, for both people and goods. But all these required advancements in mechanics, engineering, and most importantly mathematics. The British government recognized the importances of precision in manufacturing and naval navigation. Printed mathematical tables of the time were calculated by hand. These tables were used for navigational, engineering, and mathematical calculations. Mistakes in calculations and transcriptions often occurred, due to human error. Babbage was convinced that with the application of arithmetic and machinery, these calculations could be done quicker, and with more reliable results. By using a small number polynomial coefficients, he envisioned his Differnce engine, a mechanical calculator, that could compute various tables. Babbage, in 1819, began to construct a small Differnce engine, which he completed in 1822. And on June 14th of that year, he published a paper to the Royal Astronomical Society titled, Note on the Application of Machinery to the Computation of Astronomical and Mathematical Tables. The machine used a decimal numbering system and was hand-cranked. The British government took notice. And in 1823, the government gave the go-ahead with the project, along with £15,000 in funding. The design for the Differnce engine No. 1, consisting of some 25,000 parts and would have weighed 4 tons. It would use 20-digit numbers by 6th-order differences. And even though the design was feasible, the technology of the time could not produce the precision and quantity of the parts required. In 1832 Babbage produced a smaller working model, which operated on a 6-digit numbers by the 2nd-order differences. But in 1833, work on the larger engine ceased. While working on the Differnce engine No. 1, he conceived a more generally designed machine. And in 1833, he began drawing up the design for an analytical engine. This machine's input would be programmed by the use of punch cards. For the output, the machine would have a printer, and it would also punch numbers onto cards to be deciphered later. By this time Parliament was becoming doubtful of the project. They were interested in a working machine that quickly produced precise tables, not in the development of the machine itself. And after spending over £17,000, they finally abandoned the project. But Babbage persisted on, and he went on between the years of 1846 to 1849 to produce an improved design that was quicker and required fewer parts. It was designed to employ 31-digit numbers along with 7th-order differences. It would have a capacity of holding 1,000 numbers of 50 decimal digits, and tabulate various mathematical calculations, from logarithms and trigonomic functions, along with comparisons and square root calculations. He continued to make improvements in the design. Drawing of his plans of 1858 depict a regularized grid layout, similar to a modern-day CPU processing unit. That would be stored in the mill, in the form of pegs inserted into the rotating drums. There were 3 different readers for 3 types of punch cards. One for arithmetical operations, one for numerical constants, and one for loading and storage functions that transferred numbers from the mill to arithmetical units and back. Although these designs were never fully constructed, years later, in 1991, 100 years after his birth, and in celebration of his work, the London Science Museum completed a 6-year project to build a complete working model of his Differnce engine No. 2. And in 2002, they completed the printer Babbage also designed. It was constructed using the materials and the engineering tolerances available to Babbage based on the technology of his time. Throughout his lifetime, ever since the time he spent in the library of the Holmwood Academy, his studies of mathematics applicable to the real world never ceased. He wrote about his theories on industrial production in his publication titled, On the Economy of Manufactures, in which he developed a schematic classification of machines for use in factories. He described the flaws in the labor process in the use of skilled workers as opposed to delegation of low-level tasks divided among several workers to increase production and reduce cost. The book sold well, with 4 editions being published. Among his writings, in 1832, he set about to tabulate all physical constants in an encyclopedical work of numerical information titled, On Tables of the Constants of Nature and the Art. His idea of absolute measurement was the key to the development of machine tools. In 1838, he conducted studies for the Bristol and Birmingham railways, illustrating the advantages of a broad-gauge rail system. During which time, he invented the pilot, better known as a cow-catcher, to clear the railway of obstacles. In 1840 he studied the requirement for a uniform postal rate, in order to modernize the postal system, which was introduced as the uniform penny post. He also invented the ophthalmoscope, but his design was ignored. The device only came into use after it was independently invented in 1851 by the German physicist and physician, Hermann von Helmholtz. Babbage was also interested in cryptography. During the Crimean War, Babbage was able to decipher the Vigenère cipher. His discovery was kept a secret by the military, however, he published the solution to the Vigenère cipher in the Journal of the Society Arts. Although Babbage was a busy man throughout his lifetime, as a young man he married Georgiana Whitmore on July 25, 1814. They went on to have 8 children, of which only 4 survived. After his death, at the age of 79, on October 18 of 1871, his youngest son, Henry Prevost Babbage, went on to produce 6 small demonstration models of the Differnce engine No. 1, based on his father's design. One of which ended up at Harvard University, where Howard Aiken, one of the pioneers of the Harvard Mark I computer, discovered it. Many of the principles of which he applied his research to construct the Mark I computer. Babbage's concept of digital programming for use in mechanical computation led to the machine languages in use by computer systems to this day. His vision of the potential of a machine capable of precise calculations and the means to build such a device is a testament to his determination to bring it to fruition. And although he never succeeded, others picked up where he left off. His inspiration resulted in the advent of the age of computers. If not for his pioneering efforts, what we call technology, and the world we live in, might look very different today.